So, dear students, welcome back after the break, and before the break we are discussing about common base amplifier and common gate amplifier. So, this is the example of that common base amplifier. In fact, we are covering the numerical examples, and we already have discussed this circuit. So, likewise we also have discussed common gate amplifier. So, here we do have the common gate amplifier, and next to this common gate amplifier, what we are looking for, it is you might have observed that at the gate we are connecting one capacitor Cg. In fact, if you see the previous circuit, so there also you can see that in common base amplifier, here also we do have the Cb that makes the base node AC ground, and with that assumption we have done the analysis. Now, it is very important to keep this capacitor sufficiently large, so that the base node, particularly for the signal, it should be working as a ground. And this is important specifically for common base. In fact, this is also important for common gate, but since the discussion it will be similar, here we are going to talk about performance of the common base amplifier without this Cb, without the Cb. So, in our next example, numerical example, that is what we are going to do, and we will see that what are the performance degradations are happening due to eliminating this capacitor. So, you can see that the base node we do not have any capacitor, and rest of the things it is very similar to whatever the numerical example we have discussed before. So, you may recall the voltage gain if we have the Cb connected. So, if I say the expression of the voltage gain with Cb, it has been enlisted here. So, this is the voltage gain from the emitter node to collector node, and this is the expression of the input resistance of the main circuit looking into the emitter terminal. In fact, if you consider Re, we should also consider Re coming in parallel, but what is most important thing is that the main device, we do have the R pi, and then we do have the input impedance coming from the active circuit. So, that is it is given here, and so that is a small notation correction. Instead of C R1, we should write RC here. So, same thing, this is RC, this is RC, rest of the things are okay. So, this was the expression whenever we are connecting the Cb. Now, if I remove the Cb, what will be the consequences on these two important parameters, namely the input resistance and the voltage gain, and maybe the output impedance also. So, that is what we are going to discuss now. Now, let me draw the small signal equivalent circuit, of the main amplifier, try to explain that what kind of effects are there. So, this is Rc connected to AC ground. So, this is Rc, this is also Rc, this is also Rc, and here we do have Gm into VBE, voltage dependent current source, and then of course, we do have the Ro, and then we do have the Re connected to ground, and at the emitter node we are feeding the signal through the signal coupling capacitor, and let we have its source resistance is also there, say R s. Now, what is the, so this equivalent circuit we already have discussed. In fact, we also have discussed that the voltage across this R pi, it is VBE. So, this is plus and this is minus. Now, earlier this node it was AC ground, but if you look into this circuit, we do have R A and R B, they are together, namely parallel connection of R A and R B, they are forming the Thevenin equivalent resistance, and for the small signal what we have to do, we have to consider this R A in parallel with R B. But then definition of the VBE, still it is the voltage across this R pi. Now, as I said that if we are considering CB, then we do have this expression, and if you see here the basic difference, here the VBE it is not same as whatever the emitter voltage we are having. In fact, earlier in presence of CB, the emitter voltage it was same as minus VBE. On the other hand, the VBE, it is of course, it is the function of this emitter voltage, namely VBE equals to minus VE multiplied by R pi divided by R pi plus R A in parallel with R B. In fact, if you look at this circuit carefully, if we have VE here and the voltage available across this R pi, it is nothing but the potential division of whatever the emitter voltage you do have. And due to this, whatever the GM into VBE we do have, this part can be replaced by GM into R pi divided by R pi plus R A in parallel with R B. And then of course, we do have the emitter voltage VE with a minus sign. Earlier, whenever we are having a capacitor at this node, we have considered this R A parallel R B, it was 0, and then we have considered this current, it was minus GM into VE, which means, okay, so this is the output voltage, which means that whatever the derivation we do have, in this derivation, if we replace this GM, by say GM into R pi divided by R pi plus R A parallel with R B, then this equation itself it can give the voltage gain. And same thing for the input resistance also. If we replace this GM by this part, namely GM into R pi divided by R pi plus R A in parallel with R B. So, if we replace this GM by this equivalent GM, then we can get the expression of the both input resistance, then voltage gain, and then the output impedance also. So, if we recall, say, okay, so let me try to erase this board and try to plug in this expression in the expression of VO divided by Vin to get the affected voltage gain. So, what we said is this GM will be replacing by GM R pi divided by R pi plus R A in parallel with R B. So, from that we can say that input resistance R in if I ignore R e and if I consider V in by I in. So, directly we can use this equation and we can say that this is R pi in parallel with R 1 is basically R c. So, R c plus R o divided by G m into R pi divided by R pi plus R a in parallel with R b, right, multiplied by R o plus 1. And also you can see whenever we consider input resistance, earlier we are having R pi here and the base node it was connected to AC ground, and that is why we are taking this R pi. So, now this R pi, instead of R pi, we should also replace this R pi by this R pi in series with R a parallel with R b. So, if I replace this R pi by this, and then we can get the input resistance. And of course, this input resistance it does not consider, it is not considering this R e. So, if you consider the effect of R e, then both this part should be coming in parallel with R e. So, the summary is that this input resistance it is getting modified here, and also we do have this R e. Now, so likewise the voltage gain. So, we will see the voltage gain, and since we do have this numerical example, let us try to calculate what is the input resistance we are getting by considering the value of the G m, R naught, and then R c and so and so. So, you may recall for this circuit whatever the conditions we do have, collector current I c it was 0.5 milliampere, and then the G m it is I c divided by V t, thermal equivalent voltage. So, that is 1 by 52 mho, and also the R pi, which is beta times 1 by G m. So, if I use this value of the G m, we can get R pi equals to 5.2 kilo ohm. So, likewise the other parameters, say R o, which is early voltage divided by I c. So, the early voltage here it is 50, I c it is 0.5 milliampere. So, that gives us R o equals to 100 kilo ohm, and then R a and R b they are 100 k. So, we can say that R a in parallel with R b. So, that is becoming 50 k, 50 kilo ohm. Now, if I consider the middle term, particularly this term, and if you see the corresponding numerical value. So, what we have here it is R c equals to 6 k, and then R naught it is 100 k. So, we do have in the numerator we do have 106 k 10 to the power 3, and then in the denominator we do have G m into R pi, that is nothing but beta. So, that is 100 multiplied by this R naught, which is 100 k. So, 10 to the power 5, and in the denominator we do have R pi is 5.2 k, and then we do have 50 here. So, which means that this is 55.2 k plus 1. In fact, you may ignore this one part and then you can consider only the first part here. So, this is 10 to the power 5. So, in fact, I have done this calculation. So, let me share you this information. So, we do have this part, it is 0.582 kilo ohm. So, this part is 0.582 kilo ohm, and then this part, after making this replacement, we do have 50 and then 5.2. So, that is 55.2 kilo ohm, and then Re it is 10. So, this one is 10 kilo ohm. So, we do have this resistance, we do have, let me use different color, we do have 55.2 K here, and then we do have 0.582 K here, and then Re it is 10 K. So, finally, what we are getting here, it is R in very close to this 580. In fact, again here also I have done the calculation for you. So, this is 0.545 kilo ohm. So, what is the outcome here? If we are not using this CB, then the input resistance, it is quite large. Now, compared to, of course, compared to if I use CB. So, with CB, the input resistance R in, it was 1 by GM, and that is 52 ohms only. So, if you compare this one and this value, it is almost 10 order. So, it is getting increased by a factor of 10. So, intuitively what it is happening here, it is whatever the stimulus you are putting here, voltage, only part of the voltage it is appearing across this R pi, and major part it is appearing across R A in parallel with R B. So, if you see the potential division, it is happening here, and that voltage it is coming to GM into this VBE part. So, if you see the potential division, we do have here, it is R pi equals to 5.2 K, and these two resistances together, it is 50 K. So, now it is very obvious that whatever the stimulus you are putting voltage wise, only 1/10 it is coming here. So, that gives you an intuition that the equivalent GM or equivalent input impedance coming from 1 by GM, it is getting changed by a factor of 10. So, that is how the input resistance it is getting increased. So, the bottom line here it is even otherwise it is not mentioned explicitly, we have to keep in mind that at the base node we should ensure that this is signal wise, this is AC ground. So, unless otherwise you do have a special requirement, we must use the CB. In fact, similar kind of conclusion you can get for the voltage gain also. So, in the next slide, let me consider the voltage gain also. So, here again if I want to know what will be the affected voltage gain. So, we do have the affected voltage gain. So, what we can get, in fact, directly we can use this equation, only thing is that we have to replace this GM. So, let me call this is AV dash, and the GM if we replace by GM into R pi into R naught divided by R pi plus R A in parallel with R B. then we do have plus 1, and then R 1 is essentially R c. So, we can put this R c here, and then here we do have R c plus R naught. So, again here if you put the numerical value of different parameters. So, what we have here, it is Gm into R pi. So, that is beta, that is 100. So, that is 100, and then we do have R naught, which is 100 k 10 to the power 5, and then we do have R pi plus R a in parallel with R b. So, that is 55.2 kilo ohm 10 to the power 3, and probably we can ignore this one part. Then in the denominator we do have 106 kilo ohm coming from R naught and R c. So, 106 10 to the power 3, and then we do have the R c here, and R c it is 6 k, 6 into 10 to the power 3. So, that gives you a voltage gain. In fact, you can calculate this one, that gives you a voltage gain around 10 point something. In fact, I again for this also I have done the calculation for you. So, in fact, in my calculation it was 10.31. Now, of course, this voltage gain, it is from this point to this point. So, without considering R s, that is the gain, and of course, if you consider the effect of R s from here to here, we have to consider attenuation, but also you have to keep in mind that attenuation factor, it will be getting changed because the input resistance, it is not just 1 by G m, but whatever it is, the gain of the common base amplifier from emitter to collector, it is 10.31. If you recall the corresponding value of this gain with C b, it was 108. So, if you compare again this and this, almost it is a factor of 10. Again, this factor of 10, it is coming due to whatever the voltage we are applying at the emitter, almost only 1/10 it is appearing across base to emitter terminal, which means that we do have a reduced version of the voltage appearing from base to emitter, which is finally getting amplified by this. So, you can almost say that this factor, it is getting 1/10, and that gives us the gain of close to 10. So, that is how intuitively we can get. In fact, again the conclusion is that we should keep this C b whenever it is possible. So, similar to the input resistance and voltage gain, the output resistance, it is also getting affected, because the resistance at the emitter, it is getting changed if we remove this C b. So, yeah, so this is the slide to get the corresponding derivation of the R out, and the output impedance for this circuit, it is this R c. I should write here, it is R c in parallel with whatever the resistance we do have, and this is the expression we already have derived in our previous classes, and there we have assumed that the base node, it was ground, AC ground, and if you consider say the same expression, we can get the output impedance. Only thing is that this R pi we have to replace by R pi in series with R a and R b, and this is true for this R pi, this is true for this R pi, and also this G m part we have to replace by G m into R pi divided by R pi plus R a in parallel with R b. and the logic is same, namely the voltage appearing across R pi, it is a fraction of whatever the voltage we do have at the emitter node. So, we do have the emitter voltage, and then we do have the, this is the Gm into Vb, and the Vbe it is, so this is R naught, and the Vbe it is the voltage across this R pi, and now in absence of Cb we do have Ra and Rb coming in parallel. Okay. So, that is how we can get the corresponding output impedance, and so this is Rc, sorry, this is Rc in parallel with just now whatever we said, R naught plus R pi plus R a in parallel with R b in parallel with, in case if you have source resistance, we have to consider R s. Then in case if you have emitter resistor, basically R 2. So, that also you have to consider. Then we do have this part. So, let me write that here. We do have R pi plus R a R b in parallel with R s in parallel with R e, and then Gm need to be replaced by Gm into R pi divided by R pi plus R a in parallel with R b multiplied by R naught. So, this is the whole thing, that is the expression of this output resistance. So, again here also you can see the numerical calculation, and I must say, while I am writing this one, I must say that due to the present due to the absence of Cb, this part, particularly this part, the dominant part, it is getting affected because of this factor, and this factor we already have discussed that in this example it is 1/10. So, that means from here to here, this impedance, it is getting changed by a factor of 0.1, but then even if it is getting reduced by a factor of 0.1, the still the Rc it is smaller than that. So, the output impedance however, still it is remaining approximately Rc. So, internally the output impedance is getting changed in due to the absence of Cb, but the output impedance, it is, since it is primarily getting dominated by Rc and that is remaining unchanged. So, the output impedance it is remaining unchanged. So, the input impedance and voltage gain, they are getting affected by a factor of 10. So, that is about the common base amplifier, and now we will be going for design guidelines. So, what we have seen here, it is the circuit already has been designed and it is given to us, and we need to find the different performance matrices like this. Now, in actual scenario, you may have to rather design this circuit for a given requirement. So, in the next slide we will be talking about the design guidelines. If the requirement is given to us, then we can see how we can proceed to find the values of different resistances. So, the corresponding the circuit here, it is for common gate amplifier, and so likewise we also have common base amplifier, and here the task is so probably we will be having, instead of find, probably these values are given. So, Now, we do have the complementary exercise, namely the voltage gain, output swing, input impedance, maybe the current gain and output impedance, those things are given to us, and we need to find the corresponding bias circuits, and assuming the other information it is given to us. Okay. So, let me take a short break and then we will come back for this design guidelines.